and welcome to today's episode. In this episode, we will discuss about statistical quality control. The subject expert for this episode is Dr. Arshia Hussain, PhD in Human Resource Management and Teaching in Department of Commerce and Business Studies, Jamia Millia Islamia, New Delhi. And I am Sakshi Mandwal. So let us start with the meaning of plant layout. First of all, we will have a look at the meaning of quality control. Quality control refers to all those activities which are directed for planning, controlling and improving quality. It is a systematic control of management of the variables in the manufacturing process that affects goodness of the end product. The objectives of quality control are to establish acceptable standards of performance, to indicate variations or deviations, to suggest necessary changes for maintaining quality, to evaluate optimum quality obtainable under given conditions, to develop procedure for good relations between the buyer and seller. A sound system of quality control has the following advantages. It reduces cost of production. It helps in developing brand loyalty and better public relations, resulting in enhancing goodwill of the firm. It helps in increasing sales. It helps in reducing the cost of production and improves the quality of product, leading to improved productivity. It helps in developing cost consciousness within the organization. This increases morale of the employees. Inspection. Inspection is concerned with checking materials, work in process and finished products to determine their conformity with standards. It also provides data for future quality decisions and advises line management on the disposal of scrap. In-process inspection is performed at various stages of manufacturing. Its purpose is to prevent defective materials and parts from further processing. It also helps in locating the sources of the defective operations, fixing responsibility and preventing further deviations from standards. Finished products are inspected before they are dispatched to inventory control for stocking or delivery to customers. When inspection is performed on the shop floor, it is called decentralized inspection. When it is performed in a centralized location such as laboratory, it is called centralized inspection. Inspection may be on the basis of sampling or 100% units. Sampling inspection is the only practical method in case of destructive tests. Inspection procedures including tolerances, frequency, quantity and methods of inspection, instruments to be used, etc. should be carefully laid down. Inspection reports should be used for analyzing causes of deviation. Statistical quality control. Statistical quality control is the application of statistical technique for the maintenance of quality standards. It is based on the theory of sampling and laws of probability. Its objective is to control quality of materials, parts, products and processes within predetermined tolerances by the application of sampling techniques and continuous analysis of results of inspection and testing. It shows trends of quality as revealed by analysis of inspection, data and variations from prescribed tolerances, and also points up the need for preventive action for controlling quality. Statistical quality control is in almost all industries such as aircraft, automobile, textile, plastic, rubber, petroleum, telephones and transportation, chemicals and medicines. In its application, SQC is cleared in charts which indicates visually the quality of the product being manufactured. Any variation in the quality of the product beyond predetermined upper and a lower tolerable limit set by statistical methods is indicated by the chart, and action can be taken to correct this undesirable change in quality. SQC consists of both the statistical principles and charts used and the action of employees to control the manufacturing process. Thus, SQC deals with the analysis of samples and the making of inferences concerning the characteristics of the lots from which they are drawn. By employing sampling and statistical inference, it can be used to accept or reject products already produced, or it can be used to control the processes and therefore product quality while the part is being made. The following procedure is applied in statistical quality control. Establishing tolerance limits for the product, periodically testing the samples of the product, recording the results of sample inspections on a quality control chart, interpreting the records to determine whether any correction of machinery is needed. The main objectives of SQC are to check the reasonability of the already set up quality standards, to control the quality of work done during the manufacturing process, to take decision relating to acceptance or rejection of the lots of products already produced, to evaluate the processes and equipments for identifying the improvements to achieve and maintain desired level of quality, to present quality audit of the company's products to the management. The advantages of SQC are: it helps in detecting timely deviations in quality and thereby helps in identifying improvements in processes and equipment. It helps in minimizing rework costs and saving process loss due to timely detection of defective units. It helps in maintaining customer relations by ensuring uniformly high quality. It lowers the cost of inspection by using sampling technique and reduces the elements of error through oversight involved in the inspection of large quantities. It is free from personal prejudice and is very quick. It helps in enhancing the goodwill of the business enterprise by providing good quality of the products to the customers. Its operation is simple and economical because it can easily be operated even by semi-skilled operators. In case of products which lose their physical or chemical properties during testing, SQC is the only way of quality control. Despite many advantages, SQC has some limitations also. These limitations generally occur when the sample is not representative of the universe. In case the lot is of a big size, sample taken from one or few of its sections may not be representative of the lot. When sample is not representative of the lot, it is possible that a good lot will be rejected and a bad one will be accepted. If inspectors reject good lot of purchased materials, it does not harm the company, as they may send it again to the same company or another company. But the real harm is done by faulty sampling when a poor lot is accepted. It may cause production of substandard products. The objective in any production process is to control and maintain a satisfactory quality level for its product. In other words, the objective is to ensure that the product conforms to specified quality standards. That is, it should not contain a large number of defective items. This is termed as statistical process control. This is achieved through the technique of control charts pioneered by W.A. Shewhart in 1924. On the other hand, by product control, we mean controlling the quality of the product by critical examination at strategic points, and this is achieved through sampling inspection plans pioneered by Dodge and Roming. Product control aims at guaranteeing a certain quality level to the consumer, regardless of what quality level is being maintained by the producer. SQC is based on the following principles. Variability exists in every repetitive operation. The variation among various units of production is predictable and measurable. The variability from one unit of production to another is controllable within a reasonably narrow range. SQC technique can be sufficiently and successfully used only in a large-scale mechanized production. 100% inspection can be safely replaced by inspection by samples. There are two types of techniques of SQC: control charts and acceptance sampling. This is one of the most important tools of production management. Control charts are used for controlling the quality of manufacturing operations and finished products. The control chart provides a very simple but powerful graphic method of finding whether a process is in statistical control or not. Based on the theory of probability and sampling, it helps to detect the presence of assignable causes or erratic variations in the process. Control charts are used both for variable and attribute control. In case of in-process or variable control, control charts indicate the points in the manufacturing process where the quality variations are in excess of high and low tolerance limits so that preventive action may be taken. In case of quality control of finished products or attribute control, control charts indicate whether the number of rejections is within or outside the acceptable limits. Mean chart, range chart, defective chart and defects per unit chart are commonly used control charts. Types of control charts. Control charts for variables. Control charts for variables is generally based on mean or range of sample measurements. Mean or X-bar chart requires variable data. It measures the value of a characteristic. Range chart or R-bar chart also requires variable data. It also measures the value of a characteristic. Procedure. The limits are set for the process, that is an upper control limit UCL and a lower control limit LCL is set for the process. A random sample of the product or service is taken and then the specified quality characteristic is measured. If the averages of the sample of the quality characteristic is higher than the upper control limit or lower than the lower control limit, the process is considered to be out of control. Control charts for attributes. Control charts for attributes are used for acceptance sampling aimed at accepting or rejecting the lot on the basis of the number or percentage of defective pieces found in the sample. There are two methods used for making control charts for attributes. The first one is based on the proportion defective known as P chart and the second one is based on the number defective in the sample known as C chart. Procedure. First of all, a random sample is taken and then each item of the sample is inspected. The number of defective items is divided by the sample size to determine the sample proportion defective. The sample proportion defective is plotted on the control chart and compared with UCL, which is the upper control limit, and LCL, which is the lower control limit, to determine if the process is out of control. Acceptance sampling. Acceptance sampling technique is used for the inspection of purchased materials and parts and finished products. It is also called attribute sampling. It may be defined as a quality control screening procedure for lots of purchased or internally processed items. Based on the evidence about quality contained in the sample taken, acceptance sampling leads to acceptance or rejection of the submitted lots. Thus, it results in the acceptance or rejection of the lot from which the sample is taken on the basis of the number of defectives found in the sample. Acceptance sampling indicates up to how many defects in sample will be allowed in order to accept the entire lot. It proceeds by determining two levels of quality: the lowest expected percentage of defectives, which is often described as the acceptable quality level AQL, and the largest permissible percentage of defectives, often called lot tolerance percentage defective LTPD. The most important factor in acceptance sampling is to accept or reject the submitted lot. Since it is not possible to inspect physically all the lot, especially when inspection is destructive or uneconomical, then the decision to accept or reject the lot is usually based on the evidence about quality contained in one or more samples. As a result of possible sampling errors, acceptance sampling may at times reject lots of good quality, a risk assumed by the producer, or accept lots of poor quality, a risk assumed by the consumer. It is generally based on an agreement between the buying company and the supplier on matters relating to size of the sample and the percentage of defectives acceptable in the sample. The objective of acceptance sampling is to minimize the total expected cost resulting from sampling errors. Rejecting a satisfactory lot penalizes the producer by unwarranted inspection and replacement costs. On the other hand, accepting poor quality lots mean the consumer has to pay the costs of defective units at subsequent stages. These may involve high reject rates, increased rework and assembly costs for subsequent production stages, or increased repair costs and loss of goodwill if defectives are passed on to the final user or consumer of the product or service. This objective can be achieved by controlling the sample size. The maximum number of samples to be taken should be pre-decided. The sample should also define the type of measurement used to evaluate the quality of the given lot. Thus, for given quality levels and risks, it is possible to take a decision either to accept or reject a lot. Single sampling plan. Under single sampling plan, a lot is accepted or rejected on the basis of a single sample drawn from that lot. Double sampling plan. Under double sampling plan, first a small sample is taken and those with less than a certain specified defectives are accepted and those with more than a specified number of defectives are rejected. For lots falling between these limits, another sample is taken and combined with the first sample and acceptance or rejection decision is made. Multiple sampling plans. It is an extension of the double sampling plan. In multi-sampling plan, a number of samples, each of a very small size, may be taken from the lot until the cumulative evidence is conclusive enough to arrive at the acceptance or rejection decision. Single sampling plan is more popular in practice since it is easy to design, implement and understand. As compared to double sampling plan, multiple sampling plans requires fewer sample units in most of the applications to arrive at acceptance or rejection decision of the lot. Although double and multiple sampling plans require fewer sample units, but they are more cumbersome to design, implement and understand in comparison to single sample plan. Operating characteristic curve shows the working of the plan of acceptance sampling. It indicates the producer's risk of rejection of a good lot and the consumer's risks of acceptance of a bad lot. An operating characteristic curve thus quantifies the risks of accepting poor quality and the risk of rejecting good quality. In other words, OCC shows the risks of each sampling plan along with its ability to discriminate accurately between good and bad quality lots. OCC for a specific sampling plan states only the chance that a lot having acceptable quality level % defective will be accepted by the sampling plan. It, however, does not predict the quality of lot submitted for inspection, state a confidence level in connection with a specific percentage defective, and predict the final quality achieved after all inspections are completed. In this episode, we have learnt about meaning of quality control, statistical quality control, objectives of SQC, advantages of SQC, limitations of SQC, and techniques of SQC. Statistical quality control is the application of statistical technique for the maintenance of quality standards. It is based on the theory of sampling and laws of probability. Its objective is to control quality of materials, parts, products and processes within predetermined tolerances by the applications of sampling techniques and continuous analysis of results of inspection and testing. The main objectives of SQC is to check the reasonability of the already set up quality standards, to control the quality of work done during the manufacturing process, to take decision relating to acceptance or rejection of the lots of products already produced, and to evaluate the processes and equipment for identifying the improvements to achieve and maintain the desired level of quality, and to present quality audit of the company's products to the management. SQC helps in detecting deviations in quality and thereby helps in identifying improvements in processes and equipment. SQC helps in minimizing rework cost and saving process loss due to timely detection of defective units. It lowers the cost of inspection by using sampling technique and reduces the elements of error through oversight involved in the inspection of large quantities. There are two types of techniques of SQC: control chart and acceptance sampling. Control charts are used for controlling the quality of manufacturing operations and finished products. The control charts provides a very simple but powerful graphic method of finding whether a process is in statistical control or not. Acceptance sampling technique is used for the inspection of purchased materials and parts and finished products. It is also called attribute sampling. It may be defined as a quality control screening procedure for lots of purchased or internally processed items. The most important factor in acceptance sampling is to accept or reject the submitted lot. The objective of acceptance sampling is to minimize the total expected cost resulting from sampling errors. There are alternative sampling plans for acceptance or rejection of a lot. The first one is single sampling plan, the second one is double sampling plan, and the third one is multiple sampling plan. That is all that we had for you for today. We will meet you in yet another topic in the next episode. Till then, take care and goodbye.